Okay, we're ready to move on to the last section of the chapter finally. Um, I'm going to do this fairly quickly because we only have like a month of school left, believe it or not, and maybe a little more, but around that. And I want to get through a chapter on bonding yet, so we'll give you a bridge version of this. If we were actually in school, I would have ripped this chapter apart and rearranged it. This stuff I would have done first, near the beginning, because it explains why Bohr came up with his model. Your book just pretty much in the first section threw at you, hey, here's Bohr's model, and then moved on. And now at the end of the chapter, they come back and say, oh, yeah, by the way, this is why he did that model, which that's dumb. I have to write my own textbook, I guess. So, I guess the cute little intro to this is neon lights, where the neon lights glow different colors. Well, actually, neon glows this reddish-orange color. Different noble gases glow different colors. But why? Why don't they just glow like all the same color? And that's kind of what ultimately led Bohr into his model. So let's start out by talking about what is light. If we go back to the good old days, like Newton's day, they were debating, is light a wave or is light a particle? By the end of the 1600s, it became very clear that light was behaving like a wave. And so from the 1600s all the way through to the early 1900s, light is a wave, end of story. There's no question about it. So that's what we're going to go with. Now, obviously, since I'm bringing that up, there's going to be some flaws here, but let's go with light as a wave because that's what scientists pretty much were locked into for a long time of history. So, light is a wave. So here's a generic wave. This line here is the rest position. So if this is like a jump rope, this is the jump rope before you did anything. And now suddenly I'm making waves on the jump rope, and there they are. The height of the wave is the amplitude. Okay? And by the way, the amplitude of a wave corresponds with its energy. They don't tell you that here, but it does. You go to the ocean, you're hit by a tiny little wave, and it's kind of cute. If you're hit by a 3-meter tall wave, it knocks you over. Why? Because bigger amplitude means more energy. This here is the wavelength. The distance from crest to crest, it wouldn't have to be. It could be any 2 points that are in phase on the wave, but it's easy to see crest to crest. Notice, by the way, the symbol we give to wavelength is a Greek letter. Instead of just using L for length, they use the Greek letter lambda, which is their version of L. So that's what a lambda looks like. When you see it in my handwriting, it's going to look worse, obviously. But it's for waves and circular phenomena. We often use Greek letters as the variables instead of the normal Roman letters that we're used to. So that's that. By the way, notice wavelength is a length, so it's going to be measured in meters. How many meters is it from this crest to that crest? And for tiny waves like this, you might want to measure that in centimeters. Or for really tiny waves, you can measure it in nanometers, like we do for light. But it's a meter-based unit. Now, one other thing about light is the frequency. Literally, how frequently do the waves go by? So if we go back to my previous thing, let's say you're at the beach and these are the waves coming at you. Pretty skinny waves, I know. But so you're standing right here at the beach and you count these waves coming by. This one hits you, then that one hits you, then that one, then that one, then that one. Let's say that all goes by in a second. So you got hit by 1, 2, 3, 4, 5 waves per second. The next second, you're presumably going to get hit by 5 more. That's what frequency is. It's the number of waves per second. Okay? Notice the Greek letter we use for that is the letter nu. Okay, so in a math problem, if I want you to find the frequency of light, I can ask you, hey, what's nu? Okay, so the jokes don't get better when I do this at home. Frequency, notice, is waves per second, or what they say here, cycles per second. Waves and cycles aren't really units, so technically it's just per seconds, which is a weird thing to say. So what they do is they give it a name. They name it after this guy Hertz, not the rent-a-car company. So the unit of frequency, the per second, is called a hertz. So now I can say in my previous example, that wave had a frequency of 5 hertz. Okay? Now, you'll notice, and I'll go back to my wave picture, um, this wave is moving at you at a certain speed, and that's why it took 1 second to get to you, for all 5 of these to get to you. If the waves were moving faster, more than 5 would have hit you in a second. So let's for the moment assume that my waves in the ocean are not going to go faster or slower. They're always going the same speed. So 5 waves hit you every second. But what if I made it have a shorter wavelength, a shorter distance between crests? Now they're going to be crammed tighter together. But the same length is passing by, so you're going to get more waves per second, or a larger frequency. Bottom line is a small wavelength means a large frequency, because if you got tiny waves, more of them are going to pass by you in a second. If I made this wavelength really long, you can follow my cursor, like this, I maybe only fit 1 wave in a second. Okay? So big wavelength means small frequency. So bottom line is wavelength and frequency are inversely related, which, remember, we saw that back in the gas laws, where volume and pressure were inversely related. And we ended up with the 2 variables times each other equal to constant. Same thing happens here for the same reason. So wavelength times frequency equals a constant. That constant turns out to be the speed of the wave. So if I speed the wave up, then the wavelength and frequency change. So this is true, by the way, for all waves. Sound waves, ocean waves, jump rope waves, whatever. What we care about is light waves here. We're chemists, we don't care about fun stuff. So it turns out light has a specific speed that it goes, no matter what. Ocean waves have a specific speed they go depending on the depth of the water. And jump rope waves have a certain speed they go depending on the tension in the rope. So every wave has its own unique speed based on the medium that it's in. Light waves, their constant speed, we give the symbol c because we're not very creative. Actually, that c comes from a Latin word celeritas, which means very fast, because light travels very fast, strangely enough. So the speed of light equals wavelength times frequency. Again, it would be true of all waves. The speed of sound equals wavelength times frequency of sound waves. But we don't care about sound waves because we're chemists. So the speed of light equals wavelength times frequency. Notice here they show the example I've been saying. Here you have a long wavelength, and let's presume that whatever this distance across here, it's the same distance there. Let's presume that takes exactly 1 second for the light to go across there. Notice for this long wavelength, you only fit 1, 2 complete waves in. So long wavelength meant only 2 hertz, small frequency. Here you got a shorter wavelength, and you got 1, 2, 3, 4, 5, 6 waves per second. And so a short wavelength means a higher frequency, which agrees with what we just said previously. Now, here they give you the speed of light finally. So the value c, the speed of light, is this value. Notice if you round that up to 3 significant digits, it's just 3.00 times 10 to the 8th, so it's easy to remember. If you guys were actually in class, you'd have to memorize that number and use it in equations. Well, since you're at home, you can just easily write it down and it's there, right? Now, where did they get this number? Well, in part, of course, from direct observation and measurement, but also from this idea of electromagnetism. Back in the mid-1800s, a guy named James Clerk Maxwell was playing around with the equations of electricity and magnetism. And in fact, in physics, you'll learn about things called Maxwell's equations. But what came out of those equations as he was putting them together and playing around with them is waves of electric and magnetic fields. And those waves always travel at this speed. So, it turns out those waves are light waves. So, electromagnetic waves, electromagnetic radiation, if you will, is just light waves, which means light is nothing more than a ripple of electric and magnetic fields passing through space. Okay? That's why things like antennas work. They make electrons vibrate, and those vibrating electric charges generate magnetic fields, and you get electric and magnetic waves, or light waves, in that case, radio waves, which are a type of light wave. So notice they list here the whole spectrum of light. The longest waves are the radio waves. Then there's microwaves, which were once considered part of the radio spectrum. infrared light, and then visible light right in the middle of the spectrum, ultraviolet light, X-rays, and gamma rays at the very, very small wavelength end. Notice, if you go by frequency, then these large wavelength radio waves have a very, very tiny frequency. The short wavelength gamma rays have a very large frequency. But the wavelength times the frequency always equals this number, the speed of light, 3 times 10 to the 8. Okay, so I already used this term, the spectrum. The spectrum goes radio, micro, infrared, visible light, UV, X-rays, and gamma rays. But if we focus in on the visible spectrum, because that's what we can see, and spread that out, we see it's Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. Those colors, again, are different colors because they each have a different wavelength, and therefore a different frequency. And so there's the complete spectrum of light. Notice again, radio waves, long waves, gamma rays, short waves. Visible light right here around the middle, and they had to spread it out because it's really a narrow band in reality. But when you spread it out, you see the whole Roy G. Biv spread out. The lowest frequency, longest wavelength, red, is about 700 nanometers. The shortest waves, meaning the highest frequency, is the violet waves, around a little under 400 nanometers. Now, notice something interesting here. These low-frequency red light waves, they're calling low energy. High-frequency violet waves, they're calling high energy. But if you remember, I told you before that wave theory says that amplitude should mean energy. And here we're seeing the frequency relates to energy. That's a flaw in wave theory, and we're going to have to deal with that. But that's up to tomorrow's lesson to deal with that. And we'll talk a little bit more about that tomorrow. For today, I want to do a real quick sample problem using this wavelengths of light, so you can do some math problems with this. Let's say I take light of the sodium spectrum, which is, oops, I guess I need a pencil here, 589 nanometers. That's the wavelength, so I should say that equals lambda. It's really tiny, I should make it a thicker line. That's the wavelength of the light emitted by a sodium atom. So if you look at sodium vapor lamps, like a lot of, what are they called, street lights, use sodium emission. Those street lights, the ones that have a little yellowish tint to them, this is the exact wavelength of light that those street lights are emitting. Okay, so my question is, given that wavelength of light, what's the frequency of that light? Okay, well, speed of light equals wavelength times frequency. My lambda and my nu aren't nearly as pretty as theirs, but whatever. So, notice they gave us the wavelength. It's in nanometers, we got to convert that. And they are looking for the frequency. What about C? Well, we know what that is. It's 3.00 times 10 to the 8th. There's scientific notation in this stuff, but otherwise it's just plugging numbers in. Now, lambda is 589 nanometers. Nano is 10 to the minus 9th. So decimal right here is 10 to the minus 9th. Minus 8th, minus 7th, moving the decimal twice. So 5.89 times 10 to the minus 7th. You really could plug it in the calculator as 589 times 10 to the minus 9th, and the calculator will adjust it like this for you. But I want to do it the right way because I'm your teacher and I should. So the speed of light, 3 times 10 to the 8th, equals the wavelength, 5.8 times 10 to the minus 7th, times the frequency. And so now we got to solve for frequency. How do you do that? Well, yeah, there's ugly scientific notation, but other than that, it's no different from number equals other number times variable. If you had 3 equals 5x, what would you do? Divide by 5, obviously, right? Same thing here, except it's an uglier number. So the frequency is just equal to that 3 times 10 to the 8th divided by the 5.89 times 10 to the minus 7th. And I'm going to try to calculate in time. I got 30 seconds left. Let's see if I can do it. Divided by 5.89. Okay, I get... nope, I didn't do it right. Okay, I'm out of time here. You're going to get a huge number, like 10 to the 14th. And that's going to be measured in hertz. So again, that's one problem. We'll do more sample problems tomorrow, and I'll give you some work to try tonight.